Good afternoon, everybody. Thank you for the invitation. And today I'm going to talk about probably one of the most recent research topics that I've worked on. Of course, this is a compilation of many years of my work in modeling asphalt concrete and asphalt pavements. And I'm pleased to tell you that these models and test methods they are about to be implemented in a real project. So I'm going to talk about a couple of relationships that we developed from fundamental engineering principles and application to performance engineering mixed design and quality assurance specifications. So I'm going to talk about PBR and IBR, performance volumetric relationship and index volumetric relationship, and quickly introduce you to a set of tools. It's a system of tools, and we name the entire suite of tools PassFlex. And then I'll introduce a couple of index parameters, one on cracking, one on rutting, and then show you how one can calibrate index volumetric relationship and performance volumetric relationship, and show you some of the verification results. And I'll show you the application of PBR. We do have IBR there as well, but I don't have enough time. So I'm going to talk about how we can use PBR to do performance engineered mixed design, and then quickly talk about what we are doing in performance related specifications, in QA specifications, and then complete my talk through concluding remarks. Okay, PBR and IBR. PBR is a relationship between pavement performance and volumetric properties of asphalt mixture. So pavement performance meaning life. And IBR is a relationship between index parameters and volumetric properties of asphalt mixture. PBR, in order to use PBR, you need to know the pavement design, or you can use a standard structure for the given climatic condition and traffic condition. I think good thing about PBR is that it accounts for the project-specific climatic and traffic conditions. However, probably the most challenging step in PBR development is the validation of pavement performance analysis program. That pavement performance analysis program has to have enough reliability and accuracy in order for the users to accept the results. Index volumetric relationship is based on mixture level indices, and therefore you do not need to use the pavement performance analysis program. However, because it is an index of the material, relationship to pavement performance is somewhat approximate. Okay, so what is PassFlex? PassFlex is a system of tools for asphalt mix design, pavement analysis, and performance-related specifications. And we use AMPT equipment and AASHTO test methods. And we have mechanistic models and software programs to support PassFlex. The tools and in terms of test methods, models, and programs are based on fundamental engineering principles. So it allows us to do seamless integration of mixed design, pavement analysis, and PRS. And also the power of fundamental nature of these tools allow us to develop efficient testing, but still cover a wide range of loading and environmental conditions. In order to do the pavement simulation, you do need to cover wide range of loading and environmental conditions, and mechanics allow you to do that. Distress is covered for T-cracking, both top down and bottom up, and rutting and thermal cracking and aging. So PassFlex goes like this. AMPT supports the PassFlex system. And once you're done with the AMPT test, the output files from AMPT become an input to a program called FlexMat. FlexMat is a mixture analysis program. Here, it takes the data from AMPT and do all the complex analysis with the just click a few buttons there. And then once FlexMat is done, then the output file from the FlexMat becomes an input to FlexPave on the material section. And therefore, one can do the pavement performance analysis. And the results from FlexMat and FlexPave can be used in a program called FlexMix. It's a performance engineered mix design program. And PassFlex is going to develop performance-related specifications, meaning pay tables and all those things needed in PRS. AMPT testing, you need only 6 gyratory specimens. We use small specimen geometry, so we get 4 38mm cores from a single gyratory sample, and then 3 of them are used for dynamic modulus, and another 3 small cores are used for the cyclic fatigue, and then 4 gyratory samples are used for stress strip rutting test. And these test methods are all accepted by the AASHTO, and we are currently doing ruggedness and interlaboratory study on TP133, and we are doing ruggedness study on TP132, and hopefully we can do ruggedness and IRS down the road for TP134. FlexMat is an Excel-based program. Inputs are from the AMPT machine, and it produces dynamic modulus master curve, time temperature shift factors, and then calibrated SVCD model and permanent deformation shift model. And it also produces the cracking index. We call it SAT, and the rutting index of RSI. RSI stands for rutting strain index. And it generates output files for using the in FlexPave. And FlexPave is a 3-dimensional moving load finite element program, and it accounts for the effects of loading rate and temperature on pavement response and distresses. And we use SVCD model for fatigue cracking and thermal cracking, and permanent deformation shift model is used for rutting. And then recently we completed the NCHRP 9-54. There we have a couple of models. One is the pavement aging model, and then AMAC model. AMAC stands for asphalt mixture aging cracking model. So those are all implemented in FlexPave. Also, seasonal effect on unbound materials is accounted for. And finally, it is coupled with the EICM, with the MERA2 weather station data and altitude correction. Right now, we are doing the reasonableness check of FlexPave version 2.0, and FlexPave version 2.0 will be in an Excel-based program. FlexMix is also Excel-based. So as you can see, FlexMat to FlexPave to FlexMix, they are all Excel-based programs, and it develops Ivr and Pbr that I'm going to talk about today. And you can do index-based PEMD or predictive PEMD using Pbr. And here we use the Bailey method, and by using these relationships, we can optimize aggregate gradation and binder content. So what are the index parameters? There are 2 of them, SAT for the cracking and RSI for rutting. So all you need to do is run AMPT test and then go through FlexMat, and FlexMat asks you what city you're going to evaluate these indices for. You enter the coordinates, and then you can quickly get the SAB and RSI values. What is SAB? SAB is that APP is coming from apparent. It's apparent damage capacity. The amount of damage the material can tolerate until the material stiffness reaches the average stiffness value scaled by a modulus factor. It's like amount of damage a material can tolerate until certain condition near to the failure. And SAP value varies between 0 to 50. Higher SAP means better material, and it accounts for the resistance to deformation, damage characteristic, and failure criterion in a single parameter. You see on the right hand side. Okay, so SAP has uh, resistance to deformation through time temperature shift factor and dynamic modulus, and also damage characteristic like alpha C11 and C12 from damage characteristic curve, and finally failure criterion. So fatigue cracking is related to how much of resistance the material can have against the load, and also how damage evolves through the cyclic loading, and finally when the failure occurs. So we were able to put together these three mechanisms into a single parameter called SAP. On the routing side, we were motivated by the calibration data that we have. If you look at the measured total rut depth versus predicted rut depth from FlexPave of multiple projects, we actually have a very good relationship. And by the way, this correlation between measured and predicted, uh, you know, we simply got the original materials used in these test projects, ran AMPT SSR test, and then plug them into FlexMat, plug them into FlexPave. There's no correction factor, nothing, and we were able to get pretty good relationship between measured and predicted. So based on this motivation, we came up with this rotting strain index. And basically, we are dividing the asphalt concrete layer into sub layers. And we know temperature changes along the depth of the pavement, also time of loading changes along the depth of the pavement, also vertical stress changes along the depth of the pavement. Okay? So by doing analysis of the viscoplastic based shift model for each sub-layer. And then once you know the permanent strain in each layer, we multiply by the sub-layer thickness, sum them up to get the rut depth. And RSI is simply average permanent strain for the asphalt concrete layer. So rut depth divided by the summation of all the sub-layer thickness. So RSI, rotting strain index, is an average permanent strain for the given asphalt mixture. So good thing is that the rotting strain index considers use condition in a more realistic manner compared to something like flow number, where you get a kind of snapshot behavior of the material. We actually get the material performance under different temperature gradient and loading time gradient and stress gradient and everything. Okay? So we account for distribution of loading time through depth and stress distribution through depth and temperature through the depth of pavement and variation in temperature throughout the period of service, because EICM is connected to FlexMat to calculate the rotting strain index. However, we have to use a standard structure in order to expedite the process. Otherwise, we would just use FlexPave, you know. So in order to make the calculation fast, we adopted these three standard structures. So if you have a surface mix, then you'll be choosing this structure. If you have an intermediate mixture, then intermediate coarse mixture, then you'll be selecting this structure, and base mixture, you'll be selecting this structure. Okay? So for these standard structures, once you enter the AMPT test data, then it's going to do all the calculations in FlexMat. And I'm going to show you how these SAP and also RSI predict the effects of different mixture factors. Okay, so we look at 3 different mixture factors here. First one is the air voice. And what you see at the top is the flex pave simulation. This is a full-blown flex pave simulation. On the left-hand side is cracking. On the right-hand side is the rutting. And bottom here is index value. So you see SAP here, and you see RSI. On the left-hand side, these are all index parameters. Left-hand side is for cracking. Right-hand side is for rutting. And these CALU 70 and CALU 50, they are coming from Bailey method, representing 2 different gradations. In this case, these are both fine gradations. And as you go from this to the right, air voice increase. Okay, so same asphalt content, same gradation, but as air void content of the test specimens change, and as air void goes up, damage goes up in both gradations, C50 and C70. Same in SAP. Higher SAP means better. So as you increase the air voice, fatigue resistance becomes poorer, SAP value goes down, and that can be seen in both gradations. If you look at the rutting side, as you increase the air voice, rutting increases in flex pave, and also RSI increases in the index parameter. Effect of gradation, here everything is kept relatively constant, but gradation actually changes. As you go to final gradation, damage decreases, and also SAP value increases, and also rutting decrease. In this case, you see, it's actually opposite to what we see in other mixtures, but all other conditions, actually rutting increases as gradation becomes finer. Okay? And same trend can be seen in RSI values. Effective asphalt content, we have 4.5 versus 5.2. As you increase the asphalt content, percent damage decreases, SAP increases, and also this is rutting side. Increasing asphalt content increases the permanent strain and also increase the RSI. So it's just a snapshot of the data I'm showing you here, but we have enough data to be able to say that both SAB and RSI seem to reflect the effect of these mixed factors properly. And we have test results from over 100 different mixtures. So we were able to use the intended use of those mixtures and develop these threshold table for SAB and RSI. So if traffic level less than 10 million ISOs, SAP has to be greater than 8, RSI has to be less than 12. So RSI is the maximum value, SAP is the minimum value, and heavy traffic between 10 and 30, we have another category and so forth. Okay? So if you have a mixture for your region, by the way, these over 100 different mixtures are coming from all over the United States and Canada, and some from Asian countries and whatnot. So it covers a wide range of conditions. However, if you have a locally specific traffic condition and climatic condition, you may be able to test your mixtures and refine these threshold values. Okay, so I've been talking about performance. So what about volumetric side? Okay, so on the volumetric side, we use this so-called in-place VFA versus in-place VMA. These are the 2 volumetric properties that can capture other volumetric properties together. And what you see here is these rectangles represent similar gradation. Okay, similar gradations. For example, if you have a paving project, probably you'll be in one of these rectangle here. Okay. Now within each gradation, as you go from bottom right to top left, in-place density goes up. So low air voids here, high air voids here. Okay? And within each gradation, as you go from left to right, binder content actually increases. Okay? And also gradation-wise, going from here to the right, if it is a fine gradation, then it becomes finer. And if it is a coarse gradation, it becomes coarser. Okay? So if an agency has limits on their volumetric properties, then you can actually define these rectangles. And then we use so-called four-corner concept. And there's a publication by David Wang couple of years ago showing why four corners, not three, not five. But we found out that if you select these four corners, okay, and fabricate specimens at these four corners and run the performance test, then you can predict what happens to inside of these four corners. You can predict what happens to the material with these volumetric properties by using performance data from these four corners. Okay? And this paper talks about why four corners and so forth. Okay? So what we do to calibrate Idr and Pbr is that when you have a mixture, then we identify these four corners and then fabricate specimens, run AMPT test, go through FlexMath, go through FlexPave. Now FlexMath, we get the index values directly without going to pavement analysis. So knowing VMA and BFA in place and performance from FlexMath, index values from FlexMath, I can develop IVR, index volumetric relationship. It's not shown here, but it's actually a linear relationship. Okay. However, if you know the pavement design, then you know the climate, you know the traffic, you know the thicknesses, you can enter this pavement design information to FlexPave with the material properties coming from four corners, and then you can develop PVR by using volumetrics from here and also pavement performance coming from FlexPave. Okay? So that's PVR. So if you're interested in IVR, you can stop at FlexMath. If you're interested in PVR, pavement performance volumetric relationship, then you go all the way to FlexPave. Okay? So let me give you a few examples. I'm going to go quickly here. Kalu here meaning different gradations. Kalu 58, that happens to be the superpave volumetric mix design. And in this case, I chose these four corners and predict what happens to the performance of the rest of the points. Okay, so these four are the calibration points, and the remaining points are verification points. And here are the results. So this is verification of PVR. So what you see in the x-axis is percent damage calculation from FlexPave, and y-axis is percent damage predicted from PVR. And these four circles are calibration points, and therefore they should be on the line of equality fairly well, because I use these 4 points to develop the PVR, and therefore when you predict percent damage from FlexPave, it should match quite well. And these crosses are verification results, and they seem to be along the line of equality here. On the rotting side, this is the percent average permanent strain from FlexPave, and this is RSI from PVR. This is percent average permanent strain from PVR. And again, calibration points tend to follow the line of equality as well as the verification points. And this was the surface mix, 9.5 millimeter nominal maximum aggregate size with PG64 minus 22 with 50% RAM. And here's the IVR verification, because you get the 4-corner data and you can do IVR, but you can use same data to do PVR. Okay? So here IVR, here's the SAP predicted from IVR, SAP calculated from FlexMat, and again, calibration points are along the line of equality as well as the verification points. This is the RSI verification. Although there's a slight slope there, in general, they follow the line of equality quite well. This is another example. Maine DOT had a real construction project, and we were able to collect production samples and use these 4 points as the 4 corners. Some of the points were tested by Maine DOT, some other points were tested by NC State. And here, again, calibration of 4 points and verification of the 6 points seem to follow the line of equality quite well. This is another case of RS 9.5B, 30% wrap in this case. In this case, I chose these 4 as the 4 corners and predict what happens inside of the 4 corners, but also outside like this. Okay? And this kind of prediction is important in PRS because the in-place density sometimes can be lower than 93%, and we should be able to predict the performance of those mixes as well. And again, PBR prediction looks pretty good. IVR, I don't have IVR here, but PBR actually look pretty good here. Okay? So how do we use this information in PEMD, Performance Engineered Mix Design? PEMD is simply a process to get the optimal combination of aggregate and asphalt binder for the given level of traffic, climate, and pavement structure. But this terminology, PMD, it captures the desire to improve performance and advance the state of practice beyond balancing two distresses toward an approach to integrate mixed design, pavement design, and performance-related specifications using fundamental engineering principles. And we use Bailey method in PEMD. So if you have an existing gradation, then we use Bailey method to widen the gradation. So you get this green and you get this red gradation. Those are 2 gradations that we'll be testing. And then we do something similar to superpave volumetric mix design. We get these 4 points compacted to end design. And then because we are interested in 4% air void as the target mix design air void, we end up choosing these 4 points. So those 4 points become the 4 corners in PMD. And because you know these 4 corners, now you can fabricate specimens, run AMPT test, do FlexMat, go to FlexPave, and get the PBR and use this PBR for PEMD. If you stop here and use index value, then use IVR, and you will be able to do index-based PMD, which I don't have time to show you today, but you can actually do the predictive PMD using FlexPave, or you can use index-based PMD using FlexMat. And this is what you get, because we can predict the mixture performance at any point within this rectangle. So what you see here is the live contour. Okay? So cracking, as you go from left bottom to top right, cracking resistance becomes better. So you see more green up here. Okay? And low VFA, like not enough asphalt binder, you get this red. Rotting side, on the left-hand side is green and right-hand side is red. Okay. So you get these live contours from the PBR. And once you have these live contours, then you can overlap these 2 live contours to determine minimum live based on rotting and fatigue. Okay? And when you do that, down here, this was governed by cracking, and up here, it was governed by rutting. And you see this green belt here. And this green belt has the largest or longest life here, 16 years, 15 years, and so forth. Okay? But in PMD, we are not interested in all the volumetric conditions, but we are interested in the optimal design at the target air void of 4%. Okay, so we can actually get a strip of information at 4%, and now back to percent air void versus percent AC plot, and this is the 4% air void strip out of this contour. Okay, now you can see there's a zone of volumetric or asphalt content that gives you about 4% air void and gives you the longest life of around 15 years. Okay? So once you know that, then we can use the flex mix program to calculate the stockpile contribution from different aggregate stockpiles. And we have 3 different candidates here for 3 different gradations, color 54 to 58. Color 54 requires, that's a finer mix, 6.3% optimum asphalt content, and you need to have these proportions from 4 stockpiles. So flex mix program actually does this for you so that you can get the final candidates for your use. And we did the quick comparison between the superbay volumetric optimum versus predictive PMD optimum. Asphalt content increased, and superbay volumetric optimum fatigue life was 6 years, rotting life is 20 years. But when you combine them together, of course, fatigue cracking governs. So that superbay volumetric optimum will have 6-year life, but by balancing fatigue and rotting together, we can get the 14.7 years, and there's about 8.7 years of increase in performance by doing the PMD. And we've done the same thing on 50% wrap mix. Here, because it is a 50% wrap, rotting, you have no problem whatsoever. Okay, it's all 20 years. Fatigue cracking governs in this case. And when you look at the 4% air void region, you basically push to the highest asphalt content because this mix is very brittle, and we need to put more asphalt to get the balance between cracking and rotting. Now, finally, how do we apply this to performance-related specification? This is probably a little bit too complex for some of you, but just bear with me. I have about 3 or 4 slides here. PRS, you need to build a material database first. So maybe you can do PMD on multiple mixtures. And when you have, when you build the material database, you select typical mixtures that you use in your state. And then you do gyratory compaction, run AMPT tests, go through FlexMat, and you store FlexMat data, modulus cracking and rotting data for 4 corner conditions. Okay, so basically what we do is in North Carolina, there are different mixture categories. So in each mixture category, we identify some common mixtures, and then we run AMPT tests on 4 corners of those common mixtures and store modulus data, cracking data, and rotting data, and that becomes the local material database. Okay? And once you're ready to develop PRS, then now you have the pavement design here. So you know the pavement design, you know the structure, you know the climate, you know the traffic. So material properties, you enter 4 corner data here, 1 by 1, okay? And then go through the flex pave, and now you have the performance of that pavement for each of the 4 corner data, okay? So you do this 4 times, basically. You have 4 corner volumetric conditions, and you get the 4 corner performance. And by combining these 2, you can develop the performance volumetric relationship. And once you have that, you can actually look at the as designed versus as constructed and apply the cost model and develop the pay table. Okay. Now, once pay table is developed, in actual construction, you don't need to do the performance testing. What you need to do is measure in-place density or some of the volumetric properties, and those are the AQCs. And then you come to the pay table directly. Pay table is based on volumetric properties and determine what the pay factor should be. Okay? So PBR, the main reason for PBR is to avoid performance testing during production. Because performance testing during production, I don't care what kind of performance test you have, you need to compact specimen, you need to run the test, and therefore it's not possible to test every single sample, QA sample, through the performance test. So we do that through the PBR and develop the pay table based on volumetric properties, so that in actual production, we do the same thing that we've been doing. In other words, we measure in-place density, we measure the volumetrics of a QA sample, and then come to this pay table to determine the pay adjustment. So that's the main reason for development of PBR in PRS. And pay table looks like this. This is one example of North Carolina surface 9.5 millimeter mix. And depending on the EMA value, you have different tables. And green means better payment than the red, and red means it's really fairly large penalty here. Okay? And now we have the so-called protocols, PRS protocols. There's no way I'll be able to explain what this flow chart means, but if you look at the big component here, this is where we develop local material database. Okay, we develop local material database. Once you have actual PRS project, then you go through IVR or PBR analysis with the reliability and risk analysis and develop pay table. Okay, and then the contractors will bid and submit their mix design, and that mix design is going to be approved through AMPT performance test using SAB and RSI threshold values for the given traffic. If it does not meet the threshold value, then contractor has to resubmit the mix. And once mix is approved, you go to the production, and here we do the conventional AQC measurements, in-place density, binder content, BMA at end design, and use this pay table over here to determine pay adjustments. Okay. And we have different scenarios, like 8 different scenarios like this. So depending on the agency's needs and interest, they can select something very simple to very complex to do their QA specification. And this is programmed in PassFlex. So PassFlex is not just the system of tools, but PassFlex goes through this entire flow chart and develop pay tables for the agencies for their use. Okay, so 7 RSI, the index parameters from AMPT test, and also PassFlex system does all that automatically for you. And we have demonstrated in multiple mixes that changes in SAB and RSI as a function of air voids, binder content, and gradation match the common understanding of their effects. Okay. And IVR and PBR calibrated using 4-corner data have been verified using multiple mixtures so far. And PEMD allows the balance between cracking and rutting by optimizing aggregate gradation and binder content. Okay. And also IVR and PBR allow the acceptance and pay adjustments in QA specifications based on conventional AQCs. And therefore, in production, you do not need to change what you're doing, but we use IVR and PBR to make that happen. And PassFlex provides seamless integration of mixed design, pavement design, and performance-related specifications. I know I kind of went over, but hopefully we have about 13 minutes to entertain any questions if you may have. Yeah. Thank you.
Thank you, Professor Kim, for that presentation. It was very exciting, and it's beautiful to see how everything comes together. I had the first question for you.
Mhm.
I would like to know if this has been implemented for SMA and how is it different in that case?
Okay. Yeah. Sorry. Got the problem here. Oh, okay. So SMA, we are currently working with the, oh, no, Maryland DOT, but that mix is not SMA. I don't think we have tested SMA yet, but I don't see, well, I haven't tested, so I'm not going to speak how it's going to work, but we haven't tested SMA, but we've tested coarse graded mixes and fine graded mixes of different kinds so far. Yeah.
And could you elaborate on how you envision it would change? It would have to change, or no adjustment would be have to made to the framework?
Framework itself, I don't see that the need of change. Uh, so you're talking about PMD framework here or PMD framework, right? Yeah, I don't. Well, again, I wouldn't say without the data. So I'm not going to extrapolate my experience here. But uh, I mean, theoretically speaking, there is no reason to change the framework. You know, framework remains the same. I guess big question is how do we predict the SMA performance in the field?
Thank you, Professor. We have three in line. I think Egemen was the first to raise his hand. So Egemen, if you want to unmute your microphone, you can go ahead. I see you unmuted, but I cannot hear you.
Well, can you hear me now?
Yes, I can hear you now.
Okay. Well, thank you very much, Professor Kimball. That was very interesting. My main question is how sensitive is the intermediate points to your selection of the four corners, and how do you will select the four corners? I guess that's the next question following that.
Okay. So four corner selection is based on your state agency's QMS quality management systems manual. So we go there and then we look at the widest range of volumetric properties that your QMS allows, and then we test for. But it really depends on what you are talking about. Like PMD, my PowerPoint somehow I turned off. Let me get back to that. And oh, uh, just one second. So four corners. I mean, any of these examples is fine. Yeah. So here you see, in this case, This is 70. You see the
share your
first
screen, Dr. Kim, please?
Huh?
Can you share your screen?
Oh, I'm sorry. Yeah. Okay, you see now?
Yes.
Okay. So in this case, we chose these four corners. And you see the first number, C70, these are all one gradation. Okay, Kalu number, coarse aggregate loose unit weight of 70, all here. These are all C50, so this is the final gradation. Okay, and superpay volumetric happens to be C58, right? So in this case, I chose these four, and we are trying to predict the performance of these as well as these two. Now, in this case, this C50 and C70, oops. Do I have the gradation for that? No, I don't. Okay. But probably it won't be very different from the range you see here. Something like this. Yeah, actually, I think this is the same data. Yeah. So this blue is your existing mixed design, superpay volumetric mixed design. And then we use the Bailey method to widen that gradation as much as we can. Okay, there is certain no-nos in Bailey method. So within those constraints, we try to widen the gradation. So we get this red and green. Okay, so those red and green gradations are the two gradations that you see here. Right? And the question is, can I predict? This is 3% air voids. The last number is the test specimen air void. And the first number 3 here is the mixed design air void. Okay? So mixed design was done for 3% target, and specimen was made at 3%. That's what this 3-3 means. And down here, mixed design was done for 5% target, but the actual test specimen air void is 7%. Okay? And we would like to know how well these four corner data predict like 4% mixed design with 4% the test specimen air void, and 5% mixed design, 5% air void. And this is like outside of this box, right? This is mixed design was done at 5% target, but actual test specimen air void is only 3%. This is another example, C50-59. This is C50 gradation with the 5% mixed design air void with 9% in-place air void, because this will be a problem mix, right? In the field, there's a 91% density, which is lower than typical 93% and 92% acceptance and so forth. So question is, can I predict these points from these four corner data? And it's doing actually pretty well. Okay, so what we did is we actually ran performance tests in all the points here. You see here, performance tests on all the points. So we're talking about probably half a year worth of testing here, just on one mix. Okay? And use these data from these four corners. Can I predict the measured data in the remaining points? And that's what you see here. This is in terms of pavement performance, and this is in terms of index values. Okay. I don't know whether I answered your question or not.
Yes, thank you.
Okay, the next one was Isaac. Isaac, you can mute and go ahead.
Thank you so much, Professor Richard Kim, for this very nice presentation. I have 3 small questions. 2 of them are more on the technical side. One is more about practicality. So the first question...
Let's do one by one, please.
Sure. So for this factor that is the S app that is used for the fatigue, over the years, I've been following like how this has been evolving. This S factor has been changing over the years. And I think recently the main addition to it was normalizing it with respect to E.
Right.
I wanted to ask, is there any like theoretical theoretical thing that was used in there to include this E, or it was more of a phenomenological observation?
It is a phenomenological observation. Actually, I don't think we've changed many times. There was original SAP, we call it SRAP, and then this is the final SAP. Original SAP had this numerator. Okay, then we looked at the NCHRP 9-54 data from long-term aged mixes. And those long-term aged mixes are like the aged up to 15 years worth of aging and so forth. And when we apply the long-term age data into this SAP, the trend was opposite. Not all, but some of them are opposite. Okay, so we knew that if SAP was to be used even for long-term aged mixes, we need to compensate for that additional aging that mix had. So it's a phenomenological application. I think we actually said that in the IJP paper. We found out that by dividing by this dynamic modulus with the alpha term here, exponent, we can actually even bring the long-term age data into the right trend. Okay, so you're right. This denominator was added from the original SAT, and the reason was because of long-term aged mixes. Except that actually original SAT worked pretty well, but 9-54 data gave us some warning, and therefore we had to do this. And like you said, it's a phenomenological approach rather than, but the reason that we thought about putting E star is because of the resistance to deformation. We realized that we need to include something like that in order to account for the effect of aged mix.
Thank you, Professor. So my second question is about the engine behind the Flex PAVE. So whenever you're talking about how it's done, you mentioned that there is a 3D finite element model that is in there. Right. And I would assume that for like, in order to be run millions of cycles, there should be some assumptions made in there. So can you please comment on these assumptions and their impact on the accuracy of the final results?
Yeah. So in order to get to the real bottom of this, you need to talk to Professor Godati. He's a computational mechanics professor at NC State University, and he's using Fourier transform here. And we know in certain direction we can apply the Fourier transform. So he's basically converting 3D problem to multiple of 2D problems. And let me just say it in a simple way like that, in order to expedite the computational process. And also we are dividing like a 1 day into 3 zones. So we don't do every hour calculation, but we actually have segment, and we have, there are few segmentations that we do to account for the effect of changing temperature along the year and for 20 years and so forth. So there are some simplifications that we had to do in order to make the computational time reasonable. I didn't show you the Flex PAVE prediction results, but we published that in TRV, I believe, last year. And we had the multiple field projects, and we got the original materials from those projects. So we ran AMPT, we ran through FlexMath, Flex PAVE, and showed the comparison between predicted and measured for cracking and rotting. And actually, they look really nice, really good. We need to do more of that, but at least some of the existing data seem to indicate that the program is doing pretty well.
I have a final question, but Javier wanted
sorry to interrupt. We have to officially end the seminar now, but so everybody can live to their other commitments, but if Professor Kim is willing to stay, we can
Yeah.
hang out a little bit for questions, but officially we are done now with the seminar.
Yeah, I'll be happy to stay around.
Thank you, Professor. So thank
Yeah.
you everybody for joining us. See you, and we'll stick around for some extra questions as long as Professor Kim is available.
Yeah.
Isaac, you can keep going.
Thank you.
Yeah, I
James.
just have one more question, Professor Kim. It's about more like going back to the like the origin of the viscoelastic continuum damage theory. I remember that when it was first developed, one of your first work was applying this idea on a monotonic test.
Yeah.
And this came to my mind now because let's suppose that there is an agency or there is a university or anybody who wants to test they cannot afford to buy the AAPT because they won't be able to run. While a monotonic test can be easily like it's available in most of the places, and as time-wise also it's less. So I wanted just to ask you, like, maybe, and this is an odd question, but why did you like go from a monotonic to a cyclic test, since you mentioned that there should not be that big of a difference between them?
Yeah, there's a long story and several dissertations here, but to make it short, we started with we demonstrated that monotonic and cyclic C versus S curves collapse nicely and all that. But then when AMPT came out, actually at the time it was SPT. When SPT came out, the load cell capacity was not enough to handle some of the mixes. So we had to do something because we wanted to be able to do these tests in AMPT because we knew that that was the future of asphalt testing. And it was funded by Federal Highway, and AMPT was pushed by Federal Highway at the time. So because of that, we changed to cyclic. And then now AMPT is capable of handling monotonic, even some strong mixes. But so why don't I go back to monotonic? Well, one of the problems is the failure criterion. Okay, so you have C versus S, damage evolves as load cycle continues, right? And you have to define when it fails in order to determine like number of cycles to failure or life of the pavement and so forth. But that failure criterion was developed by David Wang again, so-called DR. Okay, DR failure criteria. We had a GR, but later on DR failure criteria. And question is, can we get the cyclic failure criterion from monotonic test? That's the question. That's $1 million question sitting right there. I don't have enough time and enough resources to look into that. You're welcome to look into that. But Professor Bazan, working on concrete, is a world-renowned, mechanics professor, mostly in concrete area. Professor Bazan had some ideas about how to kind of convert monotonic failure criterion to cyclic. We kind of dabbled onto that idea a little bit during NCHRP 9-19 project, Superpave Modules project, but we never found enough time and resources to go all the way. So right now, going back to monotonic, the only obstacle we have is the failure criterion. In other words, can we get the cyclic failure criterion from monotonic test? Equipment is capable. Okay, equipment is capable, and as a matter of fact, calculation is much simpler, right? Because monotonic test, pseudo strain calculation, even damage, everything is so simple, but the problem is the failure criterion.
Thank you so much, Professor, for the presentation and for these answers.
Okay. Yeah.
Now we have Puneet. Puneet, you can unmute. Go ahead.
I'm sorry, but before you go on, let me show you the FlexPave verification validation results here. So this is actually, maybe I can use this. So we have validation sections from United States, Canada, Manitoba, Brazil. Brazil is very, very active right now. They are actually trying to use FlexPave and all the tools that I showed today for their upper level national pavement design method. So we are working with the Brazilian government and actually Petrobras and university consortium there to develop Brazilian FlexPave, and they are trying to use it for their mechanistic empirical pavement design. And some pavement from Shandong province, those are perpetual pavements, and pavements from South Korea. Over 60 mixtures, one mixed asphalt wrap, polymer modified asphalt. And here are the results. By the way, this is just straightforward AMPT testing, flex mat analysis, flex pave without any correction factor, nothing. Okay, no calibration function, just straight testing, putting into the pavement analysis program and get the percent damage predicted versus percent cracking measured from the field. Okay, and it looks actually pretty good. This is cracking side, rotting side. You saw the rotting earlier, but rotting, I was really surprised that without doing any calibration, we were on the line of equality. And pavement ME has that depth correction factor that you're applying at the end of all the mechanistic calculation, which makes it, larger E, smaller M. We don't have that problem. We don't have any depth correction factor because this is a stress-based model, not the strain-based model like pavement ME. And I think that's one of the major reasons why we didn't have to do that kind of depth correction and just straightforward testing, stress rate rotting into FlexPave, we get this kind of results. Okay? So to me, this is very important because if you go to the state highway agencies and talk about the, all the performance tests and models and so forth, in order to use those tools in their pay adjustments and all these things, they really need the models validated against the field data. So we are now trying to expand the database for field validation in the current project, but this is the data we have so far. Yeah, I'm sorry, there was a question.
Thank you, Professor. Great presentation. It was really a lot of learning experience.
Sorry, I cannot hear you.
Can you hear me now?
Kind of weak.
Oh, okay. Let me try.
Now it's better.
Okay. So thank you, first of all, Professor, for a great presentation. Really enjoyed it. I have a quick question regarding the mixes which you have shown. So I see that chosen unit weight, chosen course aggregate loose unit weight is somewhere around 70 to 50 range, which you showed. So the performance prediction is pretty much for those fine graded mixes in general, or they include coarse graded mixes as well?
Okay. So why was it 50 to 70? Because, let me share my screen. Because that was the existing SuperPave gradation.
Okay.
You see here?
Yes.
See?
Yeah.
Yeah.
So
you can do P. Oh, by the way, I guess your question is, can you cover fine to coarse, that wide range of gradation? We haven't tried, but
okay.
I doubt it. I don't think you can go from fine to coarse.
Yes. Okay.
But within fine, within coarse, I think we can, because this is the widest gradation variation that we can have.
Yes.
Within Bailey method.
Right.
And,
right.
So why was it 50 to 70? Because existing mixed design was 58.
Okay.
So we took the existing gradation, used Bailey method to stretch out to get the wider gradation range. Okay. And we actually have the data on the coarse side, and basically we are doing the same thing for the coarse.
Okay. Okay. So just a follow-up question. So So I guess then for specific type of mixtures, we need different pay tables. Like if it's a fine graded mix, we have a different pay table. If it's a coarse graded mix, it's a
Yeah.
different pay table. Or if it's a SMA type of mix, it's a different pay table.
Right.
Okay. Okay. I think, yeah, that was my question. Thank you so much, Professor.
That pay table discussion is really about this database.
Mm-hmm.
You know, so here you see in the state of North Carolina, we have these five mixed categories.
Yes.
So, I mean, this is exactly what you do in pavement ME local calibration, right?
Mm-hmm.
Pavement ME local calibration, you obtain some commonly used mixes from each category
Mm-hmm.
and then run the mechanical test and store the data in the database so that when designer needs to use the material properties, they can go into this material database level 2 pavement ME, right? And then
Mm-hmm.
design the pavement. It's basically the same concept.
Okay.
Because you got to have this database before you have a PRS. Right?
Mm-hmm.
So
Yeah.
state of North Carolina, you have 5 different mix categories. For each mix, you got to do 4 corners and
Yes.
then
Yes.
run AMPT test to develop this local material database.
Mm-hmm.
Now, so if you have an SMA or coarse or fine, I don't know how state of Illinois divides the mixes, but for each mix type, you want to choose 3 or 4 common mixes and then go
Okay.
through this process to develop the material database.
I see. Yeah. I think that exactly answers my question. Thank you so much, Professor.
So I know SMA is popular in Illinois or is getting popular. You definitely
Yeah.
need to go through this process and store the data. And then when the SMA project comes in, you already have these 4 corner volumetric conditions and 4 corner performance data. So you can actually input 4 corner material properties,
Right.
get the performance of 4 corners, and you have a volumetric of 4 corners, and you can develop performance volumetric relationship.
Right. Okay. Thank you.
So, Professor, we still have 2 questions from the chat. One is PassFlex free access? Is it available?
Okay. PassFlex is currently being built. So FlexMat, FlexPave, they are open to public. When we started doing this research, we decided to make it public domain software so that people can take advantage of our work. FlexMat, currently FlexMat 1.1.2, you can download from Federal Highway website. But we just submitted FlexPave, FlexMat 2.0, which handles thermal cracking, aging, and everything. FlexPave 2.0 is still not available, but I'm expecting within a month we can submit FlexPave 2.0. So you eventually the state of the art programs will be FlexMat version 2.0 and FlexPave 2.0. Okay? And they should be available through Federal Highway website.
Okay. And the last question I received on the chat was about the 4-corner approach. Would this approach still be reliable if we change to polymer modified mixes or if we change, for example, to SMA mixes?
Yeah. Polymer modified we've tested already and it works. So I can confidently say PMA, no problem. SMA, we haven't done it yet. So SMA, I'm going to probably be careful. Okay? I need the data to be able to say something. By the way, this IVR, we tried this on IFIT. And FI, flexibility index 4-corner works great. Only problem is effective air voice is opposite to what I expect it to be. But in terms of predictability, meaning by testing 4 corners, FI or IFIT, I can predict flexibility index of any volumetric conditions within that four corners. Yeah. And also Hamburg, we were able to do the same thing with Hamburg. So this IVR idea, I didn't have time to show, but has been demonstrated for other index properties as well.
Okay. Thank you, Professor. I think that's very valuable information. And thank you again for the very exciting presentation. It's very beautiful to see how everything comes together. Thanks everybody that stayed a little bit longer. Thank you, Professor, for staying longer. And I don't think we have any more questions.
Yeah, I'm kind of sorry that I went so fast, but you see the volume of work. This is not a small thing. It involves different test methods, ASH2 standards, and analysis programs, and field verification, and deep mix design, and construction QA specification. So you're going from fundamentals all the way to construction here. So sorry that I had to go so fast, but if you have any questions, just send me an email. And thank you for the invitation.
Thank you, Professor. I think it was easy to follow in the end, even though there was so much topics.
Okay.
Thank you again.
All right.
And thanks everybody.
Thank you.
Bye-bye.